and a very good morning. Now we are at Makmal Elektronik Asas 1 to do our practical for the assignment Common Gate Jfet. So my name is Farah Nur Adila binti Suhaimi.
My name is Nurul Atika binti Muhammad Hayat.
And I am Nurul Sofwana.
So to start, what is FET? The field effect transistor is a 3-terminal input that uses electric field to regulate the amount of current flowing into electrical circuit or electrical pulse. These are applied but in all applications at the electronic industry. So FET is divided into two categories, which MOSFET and Jfet. The Jfet is the junction field effect transistor. It uses reverse bias junctions, while the MOSFET is the metal oxide semiconductor field effect transistor that consists of oxide layer insulated from the channel and into the high input resistance.
Okay, as mentioned above, the junction of FET is a voltage control device. Okay, so the voltage appearing on the gate controlling the operation of the device. So both N-channel and P-channel devices operates in similar ways. Even as we know, the charge carriers are inverted. For instance, electrons and holes in the other. Okay, so next is the gate source characteristics.
So for the gate source characteristics, the common gate amplifier circuit is the least widely used, but still undergoes some characteristics that can be put a good use in some application. For the common gate FET provides a low impedance, but the high output impedance.
Okay, so let's go into the lab.
Gosh.
I'm going to present to you the multi-sim for my project, which are Jfet configuration with common gate. Okay, so first, the simulation were done by using the specification where the input is 10 volt, RD is 2.7 kilo ohm, RS is 1 kilo ohm, C1 is equal to C2, which are 10 microfarad. Beside, the Jfet transistor that involved was 2N3823. The connection are based on CG configuration where the gate only ground without any resistor. Okay, so here is the simulation for our project. First of all, we are going to get the value of ID from the multi-sim. This is the circuit that we obtain. Okay, so to get the ID, okay, so here is our ID, which are 2 milliampere. Then after we have done with ID, we are going to connect. Okay, then we are going to get the result of the configuration. Okay, so here is the result. In order to get the gain, we will stop this and we will put it in the peak to peak. Okay, so here is our gain. When we minus the channel B with channel A, we will get the gain. So for the simulation, we obtain the V peak to peak for both channel, and from channel B, if we divide them with channel A, we will get the result of 5.49, which are our gain. Next, we continue with the dot plot for frequency response. Okay, so the dot plot are a basic circuit for the Jfet, so it doesn't have any requirement whether it is CG, CD or CS. Okay, so this is our circuit for the dot plot for low frequency response. Okay, so graph of the frequency response bot plotter. Okay, so here 3 capacitor were added. This is the RG and this is the RSIG. Okay, so here, so this is the sinusoidal waves of the low frequency response bot plotter. The high frequency response bot plotter. Okay, so here we added 3 capacitor. Here is the bot plotter for the high frequency response with the sinusoidal wave.
So next, we proceed to calculation part, which is DC analysis and AC analysis. First, for DC analysis, we need to calculate the value of VGS. When the ID equals to milliampere, so the VGS equal to negative 2 volts. And here, we need to plot a graph, which is VGS2 against IDQ. So here, when the VGS, this is for the analysis. And for the graph, we get the value of VGS is negative 3.65 milliampere when the value of VGSQ is negative 2.7 volts. Next is we need to find the value of VDS. And the formula for this VDS is VCC minus with IDQ RS plus with IDQ RT. So we get the value of VDS is 3.7545 volts. And VS, and next we need to calculate the value of VS. VS is the negative 3.65 milli, which the value of IDQ with times with the value of RS on K, we get negative 3.65 volts. And we need to calculate the value of VD. So the value of the VD is VDS plus with the value of IDQ. Get the value of VD is 0.095 volts. VG is equal to 0 volts. And next we need to calculate the value of ID. ID is equal to VD minus VD equal to RT. So the value of ID we get 3.67 milliampere. And IS equal to negative ID, so we get 3.7 milliampere. VGS is equal to negative VS, so we get 3.65 volts. And the value of the RS is negative 3.65 millivolts. Proceed to the AC analysis. In AC analysis, we need to calculate the value of GM, ZI, Z0, and the value of the gain, AV. So to calculate the value of GM, we need first to know the value of GM naught. So to find the GM naught is 2 IDRS divided by 80, so we get 4 millis. And GM, to find the GM is GM net equal to 1 minus VGS over VT, so the value of GM is 2 millis. To calculate the ZI in RS parallel with 1 over GM, so we get 3.3 ohm. And Z0 is equal to RT, which is Z0 equal to 2.7 kilo ohm. And to calculate the gain, AV is V0 over VI or is equal to GNRT. So the value of gain is 5.4 volt, which is approximately similar to simulation and experimental parts. And this is the simulation. And for the total frequency response, we need to calculate for high frequency and low frequency. So this is for the low frequency, we need to calculate the value of FRG. We will using the formula of 1 over 2 pi of SIG plus RI plus CG. This is from this the value that we get from the frequency response in the multi-C as what include the value, and we get the FRG is equal to 15.8 Hz. And then we need to calculate the value of R0, which is RT parallel with RT. Since RT is infinity, so we know the small RT, so we equal to RT, and the value of RT is 4.7 K. And then we need to calculate the value of FRSC is 1 over 2 pi over R0 plus RL plus CC. This is the coupling capacitor for the CC, so we get 46.15 Hz. And then we need to calculate for the REQ, RS parallel with 1 over GM, and we get the 33.23 ohm. And FLS, we get the value of 238.73 Hz. The secret of the low frequency response simulation of the basic of FET. And this is the secret simulation of the high and this low frequency response output. And for the high frequency, we need to calculate the value of RTH, which equal to RSIG parallel with RG, so we get the value of 9.9 kilo. And the paper convert plots. And we need to calculate the value of CI. In order to get the CI, we need to calculate the value of CMI, so equal to 8 picofarad. And then CI, we get 70 picofarad. For the FHI net, we get the 945.67 kHz. For the high frequency output network, FH net, we need to find the RTH net first. RTH net we get 1.5 kilo ohm, while CM net equal to 2.67 picofarad, C net equal to 9.17 picofarad, and the overall of FH net we get 11.57 megahertz. And this is the simulations of the high frequency response,
which is the particle part. Let's go. Okay, this is our connection based on the simulation that have been done by Nurul. So first of all, this is the function gen and oscilloscope. Okay, this is for our connection, practical part. This is the is 2.7 kilo ohm, and this is 1 kilo ohm. For our capacitor, both is 10 microfarad, and for our Jfet, we are using 3819 because that's the only Jfet that we can find in store. the value that we get from the experimental is slightly different from our simulation due to our noise in our surrounding.
So, in conclusion, to conclude, the value of the gain from simulation in noticing and the calculation, the gain that we got of the both are nearly the same. However, there are some slightly difference in the practical measurement, and we observe that this error occur because noise of the surrounding that affect the reading of the measurement. Thank you.